parametric, uh, we like parametric equations. They're interesting to us because they can introduce a third variable. So you can say I think the most probably the context where this would be maybe the most interesting to us is if we were talking about maybe we have a ball moving, and maybe the ball is moving a vertical height, it's up and down, but maybe it also has a horizontal distance. So it's got a vertical distance and a horizontal distance, and we want to talk about where it is in relationship to time. See how there's three variables? So we have a vertical distance in relationship to time, a horizontal distance in relationship to time. So whenever we have done projectile motion problems, we could only talk about two things. We could talk about its vertical distance in relationship to time, which is how we commonly did those projectile motion problems. Or if we wanted to do a unique one, we could talk about horizontal distance in relationship to time, but we could never talk about both. With a parametric equation, you can. You can say, I've got one equation, x of t, which would be the horizontal distance in relationship to time, and another equation, y of t, that could be the vertical distance in relationship to time. You would be seeing, the graph would show the pattern of the graph you would see as like your x and your y, you'd be seeing the horizontal distance and the vertical distance, and you'd be seeing at that one time, at the next time, at the next time, at the next time, at the next time. So those individual points would be at those specific times. So it would be like the first point is the horizontal distance and the vertical distance at the same time. The next point would be that next horizontal distance and vertical distance at the next time. The next point would be the next horizontal distance and vertical distance at the next time. So you can compare those two different pieces of data at that specific time for different things. You're taking the time out of the equation. So you're taking the t variable out and you're leaving just that horizontal and vertical behind. Does that make sense? So it's kind of, it is pretty real world because we do typically have more than just two variables. And having time as like our third variable makes a lot of sense. Kind of in the way of like when we studied related rates, it made a lot of sense to have our variables relate to each other in terms of time. That's kind of the idea of a parametric equation almost, is that it makes sense to talk about other things in relationship to time. Yeah. And a lot of times, we just aren't able to do all of that because we are only able to compare two things, and parametric equations just say, oh, now we can kind of compare three. Yeah. Okay. So it says, write two pairs of parametric equations for the rectangular equation. So today, the way that this unit goes and the way that the next unit goes is there are some things that you studied in pre-calc and you might be rusty on, or there are some things that you might not have studied in pre-calc very well at all. And so what we'll do is we will look at the thing that you should have maybe learned about but might be rusty on or maybe didn't learn about at all, and we'll look at setting a foundation for it first, and then we'll look at calculus. So today we're just going to look at parametric equations. Tomorrow we're going to look at how calculus relates to those parametric equations, okay? But it's not, you have done more difficult stuff than this by far. So this is going to feel like definitely like we're taking it down a notch. We are relaxing. Not to say that we're not still in calculus, but this is, you guys have already, you have done the worst part of calculus A, B, and B, C at this point. You have it behind you. Okay, so so write two pairs of parametric equations for the rectangular equation, y equals 1 plus x squared. So the goal is to have two equations, one that is x of t, one that is y of t. So for this one, the easiest way to write the equation is to say the first one is going to be x equals t. That would be like you're just, yep, that's the first one I could write that would be super easy. And so then if your x is t, then your y would then be 1 minus t squared. So that's a good default example to like go to if they say, hey, take this rectangular equation and write it as a parametric equation. That's a good, easy way to take a rectangular and convert it. Another example, not one, not 2, we're going to write 1. Another example is you could say x equals t squared. And then if you did that, then what would y be? 1 minus t. Sorry, not t, it'd be t to the 4th. Yeah. Okay, so the way that you start it is you just say let x equal any function of t. And then you would write your y based on that. Yes. Yeah, actually, if you look, this is a mode you can change, and we have parametric. So when you graph in terms of parametric asks you for an x and a y instead of only asking for a y. And so that's what allows you to graph in terms of parametric on your calculator. Yeah. So I was showing you that in the mode of your calculator, you can switch from the function mode into the parametric mode. Yes. They should. We can compare. So here's t and 1 minus t squared. And I was doing 0 to pi because, well, let's see if it graphs that. Okay, so there is the first one, 1 minus x squared, and you can see that it was graphing this is a parabola, right? 1 minus x squared, it was graphing the parabola, but only like the right half of it, so the domain was coming into play there, of just having the positive x values. So there's the first one that we had, and then we can go ahead and graph the second one, which was t squared and 1 minus t to the 4th. And it's not graphing anything different because it just graphed it right on top. Yeah. Yeah, because your time is always positive. Well, it has negative inputs. I have to think about why. X equals t. It's because the t, because it's being squared. And so in this equation, it's being sorry, I have to think about it. Parametric equation, so functions, like graphing and rectangular, is really, at this point, I've done it so much, it's really intuitive to me. Parametric equations are not intuitive to me. I can't like think of them on the spot. So I just have to think about if we were to do like plugging in 0 for t, that would be 0. Plugging in 1, plugging in -1. I don't know why it's only graphing the right side. Yeah, maybe that would, because I had it's because of my window. It's because I had a t minimum of 0. If I did, let's do -10 to 10. There we go. There we go. It was my window. Thank you, Ellery. Ellery said, Miss Rice, come on, get your brain together. Stop acting like it's a Monday. It's not. Yes. I had my window before was 0 to 2 pi because I must have graphed a trig function the last time I did it. Yes. So t-step is saying, I'll show you guys. I'll make it a 1 instead of what it was. Make it 5. See how the graph is less curved, but it graphed really fast. Okay, so now let me change the t-step to 0.1. See how much slower it graphed, but the curve was better? So the t-step is like what makes your graph like more or less pixelated. It's like how close together your points are. Yeah. Yeah, each specific point, it's just like how far am I finding my points every 1 apart? Am I finding my points every 0.5 apart? Remember how when we were doing like when we were finding the area under a curve, we were finding rectangles. So we said it was more efficient to find less rectangles, but it was more accurate to find more rectangles. And so we have to look at, you know, kind of a compromise between the two of finding a number that is efficient but is still accurate. There's like a happy medium there. So if I want to find an accurate graph, I probably shouldn't be doing a t-step of 5 because that's not a very accurate graph, right? But I don't want to do a t-step of 0.00001 because it didn't like that 0.001. Nope, didn't like that either. Those ones are going to be the most accurate graph as far as the curve goes, but my calculator's like, no, that's too much for me. I can't handle that. So now my graph is having a hard time thinking because I'm asking it to be much more accurate, and so it's taking a long time, although it's a much better curve. So see how we're talking about the difference between your level of accuracy versus like how tedious something is and what's more efficient and that sort of thing. So putting a t-step of 5, like, yeah, I'm able to do it really fast, but my graph is garbage. But then when I start to get that level of accuracy, I'm doing my points so close together, my curve is amazing, but I'm taking stinking forever to do it, and I'm stressing my calculator out. So, like you can see, my calculator is still having a hard time. Yes, you can. It won't die, it'll just sit there and think for a long time. It'll look like it freezes and you just have to like turn it off. It happens sometimes if you have a really complicated function. The times that I've noticed it, it's like when you have a really complicated function that you're integrating on an interval and it just like won't calculate it. I've had one where it sits for several minutes before it gets the answer and it's just like sitting there calculating. Yeah. Okay, does that make sense to you guys? Okay, all right. Okay, next page. So we're going to write 2 pairs of parametric equations for this one. So what is the obvious choice? X equals t, and then that would be y equals 1 over t squared. Okay. What about if we had x equals 2t? Y equals 1 over 4t squared. Okay. Why would it be dangerous to do maybe something like y equals the square root of t? Why would that be dangerous? Yeah, because if you look at something like this, you are now messing with what your inputs can be. Does that make sense? So you want to be careful when you choose what your function of t can be because you don't want to mess with your domain by what you choose. Does that make sense? When I chose t and when I chose 2t, I was choosing a function that had all real numbers as a domain. When I chose square root t, I was choosing something that had a limited domain. Does that make sense? So here I chose something where positive and negatives can be plugged in. Here I was choosing something where only positives could be plugged in. So I might be messing with the problem by choosing something limited. Does that make sense? That could be risky too. Yeah. Okay, so what would maybe be a better choice? come up t squared. Okay, and then what would that leave us with for our outputs? Or for, yeah, for our outputs for y. Yep, okay. Yeah, yeah. Honestly, I would default to this one every time. Because why? Why do anything else? Like, yeah, yeah. Like this is the easiest one to write, so why not? I mean, yeah. And for the most part, you're probably not going to get questions like that on the AP exam because it's not calculus level anyway. But this is just like, hey, now you kind of understand how parametric equations work and how if you needed to convert. Okay. So the next one says if we have x equals 8 cos t and y equals sine cos t, describe and sketch the curve represented by the parametric equations. So this is really common, so I want to show you how we do this conversion, and then we're going to go ahead and sketch it together so you can kind of see how it works. And this one, if you were to do this on your own, you might not see it, so this is one that we memorize, okay? So the Pythagorean identity that is really common, hopefully you'll kind of recognize this, is that we have, I don't remember if it's cos squared or sine squared, but it doesn't really matter which version of it you memorize because they're the same. But sine squared plus cos squared equals 1. Do you guys remember that? Or cos squared plus sine squared equals 1, back when you guys were doing like trig proofs in pre-cal. Do you guys remember that? Sine squared plus cos squared equals 1. So what we're going to do off to the side is we're going to take this and we're going to say if we wanted to isolate the cos t, we could say x equals 8 cos t. And so then I could divide by 8. And so that means x over 8 equals cos t. And then similarly, with the sine, y equals 8 sine t divided by the 8, y over 8 equals sine t. You don't have to isolate just t. This is a unique case. This is a unique case. This is not like a typical, this is one that we memorize because we know like, oh, it's always going to do this. Okay, so I'm going to take this and I'm going to rewrite it because when you have the squared in the middle like that, sometimes it's harder to recognize. So I'm going to say this is sine t. It's being squared because that's what that notation actually means. So that's sine t that's being squared plus a cos t that's being squared. That's what that notation truly actually meant. And so now that I have that notation written down, I know that I can do some substitution. I can take the sine t out, and I know that sine t is actually just a y over an 8. So I'm going to take the sine out, and I'm going to replace it with y over 8. I have the cos t, I'm going to replace that with x over 8. So I have y over 8 squared plus x over 8 squared. That equals 1. So when you have a fraction squared, you just square the top and you square the bottom. Does that sound familiar? Okay, so this gives us y squared over 64 plus x squared over 64. And then if I don't want to have fractions, I can just take the entire equation and multiply it by the denominator. So I'm going to take the whole thing and multiply it by 64. No, I'm not. So I have y squared plus x squared, but I'm going to switch the order to make it a little bit more recognizable. So I'm going to say x squared plus y squared equals 64. And when I write it like that, do you recognize what it is? What is it? It's a circle with the center of what? It has what of 8? A radius of 8 and a center at 0. So this is a circle with radius 8, centered at 0, 0. Centered at 0, 0. So whenever you see these and you see that one is cos and one is sine, that's when you know to do it. Because these are just x and y. If it had been like x plus 5, y whatever, that's when it would be not 0, 0. That's when it would be something else. Yeah. So when these two numbers are the same, it's a circle. If they are different, then it would be an ellipse. If the signs are opposite, that's when you get a hyperbola. So these, when you see these, that's when you kind of know that it's something conic, like a conic section from pre-cal. I would say what I've noticed is that circle tends to be the more common one. So this is a circle with a radius of 8 centered at 0, 0. So what we're going to do is we're just going to go over here and we're going to kind of sketch. So we've got 0, 0. And we're going to do our radius of 8. So we're going to go to the right 8. We're going to go to the left 8. We're going to go up 8. We're going to go down 8. Okay. So there's my rectangular equation. Now, if I wanted to go back and do the parametric version, then for my parametric version, I would say, okay, I need to use my t, and I need to use my x, and I need to use my y. And for t, I'll go ahead and start with plugging in 0. And then here's 0, and then maybe I'll plug in pi halves next. And then maybe after pi halves, I'll plug in pi, that's over here. So I'm picturing just plugging in unit circle numbers, because those will be easy to plug in, right? So if I plug 0 in for x, then I would have 8 times cos of 0, and I'm just going to sketch this real quick, just the unit circle part, so we can kind of refer to it. So at 0, we've got the point 1, 0. This would be 0, 1, negative 1, 0. So I'm just kind of writing out our unit circle numbers so that we have them handy. So for x, we would have 8 times cos of 0. It would be 1, so it would be 8 times 1, which is 8, okay? And then for time is 0, we would have 8 times sine of 0, 0. Okay, so at time is 0, we have the point 8, 0. So this right here is t equals 0. So I'm just showing you how the rectangular, so we already see the rectangular, right? And so now I'm going to show you how the rectangular compares to the parametric, okay? So this point right here is specifically t equals 0, okay? So then if we do pi halves, we have 8 times cos of pi halves is what? 0. And then 8 times sine of pi halves is 8. And so 0, 8 is right here, and so this is t equals pi halves, and so our arrow is going this way. It's kind of like it would be like if the curve was a snake, right? Picture the curve as a snake. And then if you were to draw little lines on the snake in increments, the t is labeling those increments on the snake. Does that make sense? So here's my snake. T equals 0, t equals pi halves, t equals pi, t equals 3 pi halves. So, or your snake could be kind of going around like this, and then we go like t equals 1, t equals 2, t equals 3 along the snake. So it's not an x coordinate and a y coordinate. You have the x coordinate, you have the y coordinate, and then along the curve, you have your t values going along the curve. By how much time it's taking to make that curve. Does that make sense? Okay. So I think that's really interesting about parametric equations, and it almost gives you an understanding of how like the idea of time as a fourth dimension works. All right, and then if we plug in pi, what do we get? Cos of pi is, so 8 times -1 is -8, and then sine of pi is 0, and then 8 times 0 is 0. So that would be this point, and so this is where t equals pi. Okay, so there's our arrows. Yep. Okay, how are the brains feeling? What part are you not feeling good about? The time aspect. So let's say, I'm going to draw a little sketch down here. So let's say we have something like this, and we've got, we have x represents horizontal distance, and y represents vertical distance, and somebody said, okay, this is time equals 0, this is time equals 1, time equals 2, time equals 3, time equals 4, time equals 5, time equals 6, time equals 7, time equals 8, time equals 9. So then they kind of follow it. Mm-hmm. You could label it if you wanted it. But the time would just be the points. It would just be knowing that you had the first point, the second point, the third point, the fourth point, the fifth point, the sixth. It'd be this one. You would know because you'd have the arrows telling you which direction it went. Wherever they started, yeah. Whatever they plugged in. So if they plugged in 0 first, then 0's your first. So parametric could be horizontal distance in relation to time compared to vertical distance in relationship to time. So it could be shooting a basketball. It could be the height of the basketball in relationship to the horizontal distance of the basketball. You could be talking about a company, like a business of a company, and talking about your profits for one type of maybe one product and your profits of another product over time, comparing them. It could be anything. Mm-hmm. Yep. Mm-hmm. 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 Uh-huh. So you'd be like, this point has this x and y value, but it was also at t equals 2 because it's a second point. This had this x and y value, but it's also t equals 3. This is this x and y value, but it's also t equals 4. Yeah. Yeah. Does that make sense? Okay. Yeah, it's kind of wild. It's kind of weird. Okay, we got another one to look at. Are you guys ready? Okay, so it says, how does the curve represented by the parametric equation, so we got a different one this time, 8 cos t plus 3 and y equals 8 sine t plus 6. So how does that compare to the original curve? So if we take this, we're going to do the same thing that we did last time, but we're going to say x equals, I'm doing this off to the side, 8 cos t plus 3. So the first thing I'm going to do is I'm going to minus my 3 over. X minus 3 equals 8 cos t. And then I'm going to divide by 8. Because I'm still using that same Pythagorean identity of sine squared plus cos squared equals 1. I still have to use that because I still have a cos and a sine. So I've got that one, and then I've got y equals 8 sine t plus 6. So I'll minus the 6 over and divide by 8. Okay. So I'm going to switch the cos and the sine this time so that the x can go first. Is that okay? So we would have cos squared t plus sine squared t equals 1. And then we'll replace it with x minus 3 over 8 and y minus 6 over 8. So what are we going to do next? Before that. Yeah, so right the top and the bottom is squared. So we're going to have x minus 3 squared over 64, y minus 6 squared over 64, and then Reagan, you're exactly right, we're going to multiply the whole thing by 64. So what is this? It's a circle centered at 3, 6. Okay, so we're going to say circle, still with radius 8, but this time centered at 3, 6. Okay. For the next problem, they say, if you take the original curve, but change the sine and the cosine. So if you did x equals 8 sine t, y equals 8 cos t. So what we're going to do is we're just going to take the table that we did before, and we're going to trade the points so we can picture what would have happened, okay? So we're going to do the t and the x and the y, 0, pi halves, pi. So if we were to trade these, then the first point wouldn't have been 8, 0. The first point would have been 0, 8. But wait until you see what happens. It's different than that, yeah. The next point wouldn't have been 0, 8, it would have been 8, 0. And then the next point wouldn't have been negative 8, 0, it would have been 0, negative 8. So that's what would have happened if we had traded them. So I'm going to get out so we can see where we would have started. So if we had done that, then 0, 8 is up here. This would have been our first point, t equals 0. And then our next point, 8, 0, would have been here, t equals pi halves. And then our next point, 0, negative 8, would have been down here, t equals pi. So how did it change the graph? Orientation. It changed the orientation. Yeah, it started at a different point. Okay, so it changed the, we call it it's the same circle, it just changes the direction, aka the orientation, but the center is the same. So it doesn't change the center because the center, what determined the center? Can you tell? You can tell more between A and B what determines the center. Yeah, not having, because this one had like plus 0 on the end, plus 0. This one had like plus 3 and plus 6. That's what determined the center. So the fact that it didn't have anything added on the end is what made it 0, 0. So it didn't change the center. It just changed what direction it went or what orientation it had. Okay, so we're going to say it's the same circle. In fact, if we were to convert it into rectangular form, it would be the exact same rectangular equation, right? It'd be exactly the same. So it's the same circle, but it does change the direction it goes. It changes the orientation. Okay. All right, so we have some problems out of the Larson and then a punchline. Punchline. Larson is the worst.
I'm just gonna get it.